Today we're talking about how to find the tiling of an origami tessellation that you want to fold, whether you're looking at photos or crease patterns. And I've got a whole bunch of examples, but first I want to go through what is a tiling. So when we're folding twist-based origami tessellations, our twists have certain properties, which is the number of pleats that they have leaving the twist and the directions that those pleats go, that allow you to draw a shape around that twist and say all pleats leaving the shape leave the shape perpendicular to the edge. This is what is called a tile, and you can gather a collection of these tiles to form a tiling. So I want to show you really quickly a file that I have with a whole bunch of tilings, ranging from simple tilings to more complex ones, and getting into some unusual shapes as well. There's really no end to the possible arrangements of shapes. But the shapes that I use are somewhat limited because I want these things to be foldable on a grid. So I'm going to be using a hexagon, triangle, rhombus, trapezoid, maybe getting into these weirder shapes on a triangle grid, and squares and right triangles on a square or 45-degree grid, because those are the directions that my pleats can go on grid lines. And a second caveat about tilings is that you'll see here I have them drawn in two colors. We want these tilings to be two colorable so that when you have a right-handed twist, all of the neighbors of that right-handed twist are left-handed twists, and that pleat is folding over in one direction, not trying to kind of oppose itself as you go from twist to twist and having to stand up. So there's a lot of different options. There's quite a few simple ones, and we'll be going through some of the more simple ones with the physical examples, as well as some complex ones. And then I want to show you how to do this with crease patterns using the upcoming Summer of Twists ebook. So we're going to first start with our physical examples. And in this particular example, the tiling looks the same as the tessellation. So if we come back to those tilings, I'm going to look around in this file for that equilateral triangles tiling, which may not be colored in. Here we go. So we've got triangles. Each triangle has 3 triangle neighbors. There are only triangles, and you need to go around 6 triangles to get back to the one you started if you're going through the edges. So these are the properties: what shapes are used, how they're connected, and how many you need to go around a particular point. So that's equilateral triangles. I have another example in here of equilateral triangles that looks really different, but you can tell that it's the same tiling because on this side of the paper, I can see that I've got these 4 triangles and repeats of those 4 triangles. And I only have triangles on this side of the paper. And on the other side of the paper, I have those 4 triangles and repeats of those 4 triangles. And I only have triangles on this side of the paper. Now there's only one way to fit all of these triangles into a pattern, and it's with this tiling. Whenever you see a pattern with all equilateral triangles, it's in the equilateral triangles tiling. likewise with squares. So squares only fit with squares. There's not multiple ways to arrange patterns of only squares. But that doesn't mean that you can't get a little bit crazy with it when you're doing your designs. So here I have all closed square twists on this side, and flipping over I have closed and double open square twists. So it's called double open because it makes these holes on the back that are 2 grid spacings per edge. The closed twists make these closed holes. And these are all squares. They all have the property of 4 pleats. If I orient it this way, those pleats are going up and down, left and right. That's it. No matter which side I'm looking at, pleats leaving twists in this tessellation are going up and down, left and right. So for this one, for example, we have a pleat going up, a pleat going down, a pleat going left, and a pleat going right. And that's true of all of these and will be true of any tessellation in the square tiling. Now, if we look at this tessellation, also in the square tiling, if I orient it so that those squares have pleats going up and down, left and right, we see these little slits that we didn't see in the other square piece. And that's because it's using hybrid square twists. Now these might look like they're using right triangles. In fact, there is a right triangle there, but there is also a little triangle underneath. And so this is one twist where the pleats are going up and down, left, straight into that closed hole, and right. This is a square. It's just using properties of 2 different sizes of squares in the same twist. And so this also is in the square tiling. Then we have this pattern that I'm going to orient this way, even though these squares, when I orient it this way, has the pleats on the 4 diagonals. And that's because my right triangles, and these actually are right triangles, I'm going to say are defined by a vertical, a horizontal, and a diagonal pleat. So coming back to the square side, around these right triangle holes, I can see there is a vertical, a horizontal, a diagonal leading into the square. So if the diagonals are leading into the squares, that is going to make a different tiling than if the horizontals and verticals are going into the square. And I can see this is going to be, well, I'll go ahead and generate it. Actually, no, I spotted it. So with the diagonals going into the square, we have the horizontals and verticals of the right triangles connecting to other right triangles. You can see this vertical is going to another right triangle, this horizontal is going to another right triangle. And that is going to be true of all the right triangles. Only the diagonal is going to the square. And we can see that in this tiling, where the pleat that crosses this top edge of the right triangle is going to be the vertical pleat going to another right triangle. The pleat that crosses the right edge is going to be a horizontal pleat going to another right triangle. The diagonal is going into a square. We can also see some properties of symmetry that are available in the tiling. And you can never have properties of symmetry in the tessellation that aren't present in the tiling. So in this case, I could put a mirror symmetry line on any of these vertical or horizontal tiling breaks, lines that go all the way through the tiling. And what's on one side of the line is the same as what's on the other. So in this case, we actually can place those lines physically on the paper. Usually the tiling is a little bit more abstract, but in this case, it's a good example, which is why I used it for the cover image of this video, for the thumbnail. So that's what's going on in this tessellation, and it's important when you're looking at right triangles to see where is the vertical going, where is the horizontal going. And in this case, all the right triangles are acting exactly the same. In our next case, we actually have two distinct positions of right triangles. And so I'll zoom out here and go until I spot the tiling. Okay. So the tiling is somewhere on the screen. You know it's one of the ones that's using right triangles and squares, because there are both squares and right triangles in here. And one of the things I want to point out is we have these places where there's 8 right triangles around an open space, but we also have these places where there's right triangles connecting directly to a square twist. And we have these closed holes, and let me zoom in a bit on that. We have these closed holes where the pleats are going up and down, left and right, meaning that that's a closed square on the back. We can see a little bit more here on the back side of what's going on. So if we orient that closed square, so we do have the pleats up and down, left and right, we can see we've got another closed hole here where the pleats are going in 4 diagonal directions and leading into these closed holes where we have a diagonal, a vertical, and a horizontal, a right triangle. So we also have that same motif of the diagonal square with those 4 triangles around it in this tiling, excuse me, but it's not the only thing going on. So if you guessed that this is the correct tiling, then you were correct. And what we have here is our 4 right triangles around the diagonal square. Separately, we have these 8 right triangles around a common point. And we have these squares that are aligned with the horizontal and vertical of the right triangle. So this one's a little bit more complicated to put together on your own, which is why it's one of the tilings I teach inside of Tessellations by Tiles. And actually, if you want to dive deep into tilings, Tessellations by Tiles is the way to go. I have 24 about 2-hour workshops that are recorded there, ready for watching, on a whole bunch of different tilings, including all the ones we've looked at so far. So that'll be all for our exploration of square grids. I know we started with the equilateral triangles. I want to come back to the triangle grid and take a look at rhombi for a moment. So these 2 tilings of rhombi, of these 2 patterns, are not the same. And so they're corresponding to these 2 tilings on the screen. The reason they're not the same is because one of them has the potential for mirror symmetry, and the other one does not. So even though the lines in this aligned rhombi tiling go all the way through, they're not available for mirror symmetry because if you mirror the rhombus on one side to the other side, you don't get the same rhombus that's already there. Whereas with this chevron rhombi, you have these stripes of rhombi that are aligned inside the stripe. So we've got that front, back alignment within a stripe, just like we see actually over here, just at a different spacing. But then we have the mirror symmetry line to get to the next stripe. So with rhombus twists, it's really, really tempting to say, oh, the rhombus is aligned this way, therefore the rhombus that is twisted inside, or the crease pattern before it's twisted inside, has to also be aligned in the same way. And that's not the case. So you'll typically find different orientations for the tile, the crease pattern, and the folded form of rhombus twists. And there's nothing in these tilings that's saying which direction of pleats, which pair of pleats is the through line, and which one is not. So that's a note on rhombus twists. If you see mirror symmetry in the pattern, it's the chevron rhombi tiling. If you don't see mirror symmetry, well, to be honest, I haven't explored enough in the chevron rhombi tiling to know if you can do it without mirror symmetry. But yeah, that would be an interesting thing to find out. But if there is mirror symmetry, it's definitely chevron rhombi. So I want to talk a little bit about hexagons and the patterns that they show up in, where we're starting with this hexagons and triangles six-fold tiling. And in this tiling, every hexagon has 6 triangle neighbors, and every triangle has 3 hexagon neighbors. When you're going around a blank space on the paper, like this, you go hexagon, triangle, back to your first hexagon. So that's this loop around a corner. And there's no other loops. But what's special about this tiling is you don't have to use the same hexagon everywhere. You can use this hexagon that has 6 triangle neighbors, and those triangles can come back together to a different hexagon. So even though the symmetries are a little bit further out, so the symmetries in the tiling is 6-fold in every hexagon, 3-fold in every triangle. You see the same thing in 6 directions from every hexagon, you see the same thing in 3 directions from every triangle. On the tessellation itself, you can have your symmetries further out where you're seeing the same thing in 6 directions from this hexagon, but instead of 3 of the same from that triangle, you see 3 of the same from this hexagon. So 3 triangles close in, 3 triangles far out. 3 hexagons of the same, 3 hexagons different. So there's a lot of options for how you place your symmetry points, regardless of the maximum symmetry of the tiling. And then you can have hybrid hexagon twists. So this is a piece that I also taught in a tutorial here on YouTube, where if you look at it, at first you might say, that's a rectangle. But then, if you look at the back, and you see each of these little bow tie cutouts, you see 1, 2, 3, 4, 5, 6 pleats coming out. And these pleats are all going to triangles. And each of these triangles is going to 3 of these little bow ties. So this, too, is a hexagons and triangles 6-fold tiling. So the 6-fold in that just refers to the tiling, not to the tessellation itself, which in this case has a maximum of 2-fold rotational symmetry in 4 different points. So your symmetries and your tiling don't necessarily have to match, but you can't have any symmetries in the pattern excuse me, that you didn't have in the tiling. There are other ways to arrange hexagons and triangles also, and these ways of arranging hexagons and triangles were discovered pretty early on by Fujimoto when he figured out the first hexagon and triangle twists, the closed hexagon and closed triangle. So the particular way that's being used in this tessellation is this hexagons and triangles 3-fold tiling, where there's hexagons with 3 triangles directly touching them, and then the other pleats are going to go to other hexagons. So here I see my hexagon, and one pleat goes to a hexagon, the next pleat goes to a triangle. Notice 3 pleats coming out of that hole. The next pleat goes to a hexagon, the next to a triangle, the next to a hexagon, the next to a triangle. And this is the characteristic form of this hexagons and triangles 3-fold tiling. Now you can play with that, and I've done some variations on it. But one thing to notice here is, again, we have the potential for mirror symmetry. And in this particular pattern, I do use that mirror symmetry. And that's in 3 directions. So we have mirrors here, here, and here. So that's all well and good. There is another, I'm going to order these guys by how I want to bring them up. There is another way of arranging hexagons and triangles without anything else. And I didn't bring an example up here, but here we have hexagons with 4 pleats going to triangles and 2 pleats, the ones on the opposite sides of the hexagon, going to other hexagons. And here also we have the potential for mirror symmetry. So this is kind of what this tessellation could trick you into believing that it is, until you check and see, you know, actually there are 6 triangles for every hexagon, or 6 triangles around every hexagon. And none of the pleats from the hexagon are going directly to other hexagons. So continuing onwards, this tessellation is in a tiling that was one of the early ways of using rhombus twists alongside of hexagons and triangles. And in this particular tiling, I won't zoom, well, yeah, I'll zoom all the way in. In this particular tiling, it's a variant, actually, of a well-known mathematical structure, the 6-4-3-4 uniform tiling. Except instead of squares, we use rhombi. And in this tiling, there's potential for every single twist to be occupying the same global position of symmetry as the twist has local symmetry, by which I mean the hexagon can have at most 6-fold rotational symmetry, and it does in the global pattern. The triangle can have at most 3-fold rotational symmetry, and it does in the global pattern. The rhombus can have at most 2-fold rotational symmetry, and it does in the global pattern. Now, this doesn't necessarily have to be true. I have other patterns where it is not, but this is one of the earlier places of development of the use of these twists together. So when you're looking at a tessellation that uses hexagon, rhombus, and triangle twists, and you see that there are 2 of the same on either side of the rhombus, there are 3 of the same on each side of the triangle, there are 6 of the same all around the hexagon, for every hexagon, every triangle, every rhombus, then you are in this tiling. And so the way that this works is we have a hexagon that connects directly to 6 rhombi. And in this, the particular orientation of the rhombus doesn't matter so much. Like I mentioned earlier, it's basically a squashed square. So you can have it like pointy this way or pointy the other way. Like you can have them pointing around right-handed, you can have them pointing around left-handed around that hexagon. It's really not going to make a difference for the tessellation because you can just take the mirror image of the tiling and then you're back to the same tiling. Or flip the paper over. So what we've got is hexagons connecting directly to rhombi, and then the rhombus is connected to a hexagon on either side and triangles on the other 2 sides. These triangles are only connecting directly to rhombuses, and in the case of this particular pattern, it's the same distance from each of those rhombuses, those rhombi. So that is the, and one thing to notice is there is no line going through this tiling that goes further than 2 tile edges. There are no tiling breaks in this tiling. There are no places where all the pleats are heading out parallel. That is something that is a little bit frustrating as you go to fold, so you might want to check out my folding with pseudo tiling breaks video on how to deal with that. Now the alternative to using that tiling, let's see if I have it brightly colored. I do not. The alternative way of connecting things places the triangles closest to the hexagon. And this is looking like something that'll be easier to find in my regular file system. So I'll go ahead and do that. And actually, this is a chance to show you that when I'm storing my files, I'm using the tilings to organize these things. I'm very much a visual person, and so when I can have the tilings in visual form, that's much more helpful than just trying to remember names. So if we connect the triangles directly to the rhombi, we're going to end up with a different tiling that I call hex tri rom tri, as opposed to the last one, hex rom tri rom. And in this style of connection, you'll see there are lines that go straight through in all 3 directions. This means that at every step in the folding process, we can come to a stopping point where there are pleats heading out along our edge. We can always get a nice pleated border, and in general, this tiling is just a lot easier to fold in for that reason. And we have another slight difference from the previous tiling, which is that each of our corners, or rather, there are 2 distinct corners. There are corners where it goes hexagon, triangle, rhombus, triangle. That's what the tiling is named for. And then there's the corners that go rhombus, triangle, rhombus, triangle, rhombus, triangle. And on the tessellation, those are these spaces, hexagon, triangle, rhombus, triangle. And these spaces, and I call these loops in the tiling or in the tessellation. And the symmetries here are a little bit different too. The hexagon is still a position of 6-fold rotational symmetry. The rhombus is still a position of 2-fold rotational symmetry. But the triangles are not in positions of symmetry. Like if I go this way, I hit the skinny corner of the rhombus hole. If I go that way, I hit the fat corner of the rhombus hole. If I go that way, I hit a hexagon. Those are 3 different things. But this point has 3 triangles and 3 rhombus holes around it, and so that's our position of 3-fold rotational symmetry in this tiling, at least for the densest applications of symmetry to the tiling, which is, you know, the standard form. This, because the 3rd position of rotational symmetry is not in a twist, we have a lot more flexibility with choosing different options in this tiling. So we can choose hexagon, open or closed. We can choose triangle, open or closed, on the same side as the hexagon or the opposite side. Rhombus, open or closed, on the same side as the hexagon or not. That gets us 32 options, just right off the bat. And so all of these options will work at a given spacing. So if I wanted to have the open rhombus on the opposite side, I would need to space the triangles 1 spacing further out from the hexagon in order to get them to fit. But other than that, all of these options are going to work. So that's a lovely thing about this tiling. And then I want to talk about some other arrangements of hexagons and triangles. And I'll start with these 2. With this one first. So in this one we have 1 position for all the hexagons. All the hexagons are acting identically. 1 position for the rhombi. All the rhombi are acting identically. 1 position for the triangles. All those triangles are acting identically. They're each at the end of this stick coming, excuse me, got the sneezes today. They're each at the end of this stick coming off of the open hexagon. And so we have these hexagons, and it might look like the hexagon is directly connected to the triangle, but it's actually not. Each of these hexagon pleats are going into a rhombus, and then the rhombi are sending pleat 1, pleat 2, pleat 3 into the triangle. So how can this be? How can we have the rhombus and the triangle not in positions of rotational symmetry? Well, if we come over to our tilings, and yeah, there's quite a few of them even here. Here we go. We take a look at this tiling. We've got that hexagon, rhombus, triangle ring again, but then we have the exact same ring repeated over here and over here and over here. And this is something that I saw first in Miguel Gagnon's book, Twist and Tess, where you can have the hexagon, the rhombus, the triangle, and then put any amount of spacing between the next repeat. Because when the pleats are coming out of this triangle and this rhombus, they're perfect for connecting back to the rhombus and triangle on the opposite side. And that's exactly what this pattern is doing. Now there's another way of continuing that starting pattern. Notice this is the same central hexagon with the rhombi tucked under it and the triangles capping off the ends. But there's rhombi on this side, and there's these other hexagons that are not behaving that way. So what is that? Well, it's a pattern, a tiling that I call rhombus ladder, and we can see some different things going on. And this I didn't draw out enough to see the repeats of the center, but those are going to have this triangle rhombus triangle is the same as this triangle rhombus triangle in here. And so the rhombus ladder part is referring to, we have that rhombus, it's not going straight to the next repeat, it's going through another rhombus to connect to an equivalent rhombus again on the other side of the hexagon. And we've got these other hexagons that, if you look really closely, these hexagons, the red hexagons, are right-handed. These hexagons, the white hexagons, are left-handed. So we use two different twist senses of hexagon in the same pattern, which we can do because we've isolated them from each other, and we don't run into issues of like a right-handed and a left-handed twist needing to connect to, both connect to the same twist. So there's all kinds of ways of organizing hexagons, triangles, and rhombi. And you can see down in here, there's a lot more ways than I was even mentioning. And yeah, just a lot of different options when it comes to these tessellations. And I wanted to show one more while we're on the physical demos, which is this triangles, trapezoids, and big triangles pattern. And we see the same thing on the front and the back. We see these 3 triangles, and there's going to be 3 corresponding triangles on the back. These 3 trapezoids corresponding to these slits on the back, and these big triangles corresponding to that triangular hole. Now, why are these triangles a different size, though? That's because the trapezoid has an edge that is twice as long as the other edges. So if we look at our trapezoid, it has 3 edges that are the same length and 1 edge that is twice as long because it is half of a hexagon. And this twice as long edge comes with twice as much pleat depth. So we're going to have 2 grid spacings between the mountain and the valley fold on these pleats. And that means that the pleats coming out of one side of it need to be matched by another shape that has that double depth pleat. So that's where these double depth closed triangle twists come into the picture. So there's all kinds of ways to have variations on this. I'm going to bring up some different options for these mixed depth, and that is suddenly, oh, all right. Need to go to tilings to see the tilings. There's all kinds of options for these mixed depth tilings as well. So it's never something where like, oh yeah, I've found all the tilings and then you're done. No, there's always more things to be discovered, Always more options for tilings that you think you know. And yeah, just more and more and more that can be done with these twists. And most of these tilings I have not designed a tessellation for. I have designed tessellations for about 60 tilings so far. And it's just kind of crazy how they just keep coming. So next up, I want to take a look at the Summer of Twists ebook and show you another way to find the tiling, this time from crease patterns. So this is the companion ebook to Summer of Twists, which is a series of twist tutorials that I'm making for 30 different twists. Open hexagon, iso area, closed hexagon, mixed depth rhombus, these are all included. And there's 2 patterns in this book for each twist. They're not necessarily going to be in the same tiling. So as you go through, you see like the beginning instructions, introduction to the closed square twist, and here we see, okay, in my crease pattern files, I'll tell you this is in the square tiling. The other thing that you can see, so we've got the crease pattern and we've got this view of the crease pattern where I've put a dot in the middle of every twist and connected it to the next twist over that has a pleat connecting to the twist itself. So you can see this is a twist with 4 connections. It has 4 neighbors, and each of those neighbors also have 4 connections. So 4 pleats connected to 4 things with 4 pleats. That is true everywhere. This is a square tiling tessellation. And if we jump ahead, let's go to arbitrary page 50, we can see some other tessellations. This one is a hexagons and triangles 6-fold with some symmetry modifications. So you can see that the spacing is different for these 2 triangles, but that doesn't change the fact that it's in the hexagons and triangles 6-fold tiling. And if I jump to page 100, so here's a fun one. It's really similar to the small triangles, trapezoids, and big triangles one that we were seeing earlier. But this one, the double depth pleat of the trapezoid connects directly back to another trapezoid. And so we've got this tiling that I call trapezoids and 6 triangles. The tiling. The pattern is dancing pyramids, if I remember correctly. Yep. And so just going to take the scroll bar and jump down a ways. This one's another hexagons and triangles 6-fold, and all of the hybrid hexagons are going to be in that. Here we've got a very interesting hybrid square twist, which is going to be used with other square twists in a square tiling. If we go, let's see, all the way down and a little further. Okay, so these mixed depth twists can still be used in standard tilings, but they don't have to be. So this one uses 3 double depth triangles and 3 single depth triangles all around these 3-fold mixed depth open hexagon twists. But if we go down to the next example, this is using a tiling that I call pinwheel hexagons 3-fold, or pinhex 3 for short. where we have a hexagon going to triangles, going to, looks like a rhombus, but it's not because it's got this double depth pleat. That's actually a closed trapezoid. That's then going into, so the double depth pleats and a single depth pleat of the neighboring one are going into this mixed depth hexagon. And again, we can double check our assessment of these twists by seeing, okay, these are the ones that are actually twists. Going down to that second page of the document of each crease pattern that I produce and seeing the skeleton form that says, okay, I have dots in every twist. I can see how many pleats are leaving the twist and in what directions. And for this trapezoid, for example, I can see like, okay, I have 1, 2, 3 single depth pleats, and they are 3 kind of next to each other. And then I've got that double depth going the opposite direction. That is classic trapezoid behavior. You can continue down and see like this mixed depth rhombus or double rhombus can be used with copies of the same thing. No mirror symmetry. This is going to be the aligned rhombi tiling, which actually looks remarkably like the square tiling in the skeleton form, because it's the same idea, like 4 square neighbors, each with 4 pleats, and it's basically a smushed square tiling. But then you can also use it in this tiling where we have the hexagon going straight to the rhombus, which is 3 rhombi around a triangle. So this hex-rhomb, tri-rhomb tiling. And here you can really see the symmetry even in the skeleton as well, where we've got this hexagon outline, which is the repeating unit. Whenever you have hexagonal type symmetry, you're going to have a hexagon outlined by those positions of threefold rotational symmetry at the corners. And that's going to be your repeating chunk. Now, it's not so easy to draw things with just that repeating chunk. And I have a whole bunch of videos on drawing crease patterns with different symmetry types. So that's what's going on with tilings, with seeing all of these different options. So if you'd like to get the Summer of Twists ebook, make sure to go to training.gatheringfolds.com/summer, and you can either sign up for reminders or see the link directly for the ebook from there. And that is all that I have to say about the tilings. I'm going to check back in. And thank you, Nancy, for answering the question about the software. That was indeed Inkscape. And yeah, that's what's going on with the tilings. So when next week, I'm going to be talking about not just identifying the tiling, but also folding, using the tiling as a guide. And this is something that I've talked about a little bit in previous videos. But that's something to look forward to in the next video. So happy folding, everyone. Go check out Summer of Twists, and I will see you in the